Hello and welcome to technically the last lecture of Introduction to Astrophysical Fluids. So in this lecture, we will continue our discussion on astrophysical dynamos, and in previous lecture we just introduced the concept of the necessity of dynamos and why basically we need to think about a dynamo type of mechanism. Okay, and we actually saw that there are two parts of the game. One is that to produce the magnetic field, some large scale magnetic field starting from some seed magnetic field, which is caused by the statistical fluctuations of magnetic field in a plasma. And then once this is produced, okay, and that is produced by some instability, and once this is produced, the question is to sustain that, okay, so that we can see the magnetic fields as they are in the common astrophysical systems. And we talked about three typical systems. One is for the star, one is for the earth, and of course the third one is for the spiral galaxies. Okay, we mentioned about the pulsar magnetic field, but this is which is quite strong, and this is the story is even quite complicated. So in this lecture we will give you a very basic qualitative idea of how a proper dynamo action can be understood. Okay, but before that we will start by a very interesting theorem which rules out some possibility of having a dynamo action under certain simplistic condition. So this theorem is known as Cowling's anti-dynamo theorem, because Cowling was the first one who gave this theorem. And here we mainly investigate whether kinematic dynamo action can be obtained from the induction equation of an incompressible MHD fluid where the velocity is given. So once again, for recapitulation, kinematic dynamo means that we will try to solve the induction equation so that velocity is given and velocity does not, magnetic field evolution, the just evolution equation is just a linear equation in B, and the magnetic field does not give any feedback to the velocity field through the Lorentz force. Okay. Now in this situation, if we again take for simplicity a very particular situation where we imagine that we have a steady axisymmetric given velocity field. Now the question is that whether this type of velocity field can sustain a steady magnetic field which is also axisymmetric and about the same axis. Now whether this is a possibility or not, this is possible or not. So by Cowling's anti-dynamo theorem, one can actually show that this is not possible. Now how to do that? Cowling's original proof was not really very rigorous, but there is a short but much more rigorous proof of that, and we are now trying to follow in this lecture this proof. So since both B and V, that means the magnetic field and the velocity field, B can actually be written correctly as capital B, yeah, because here we will use everywhere capital B. Okay, capital B and V fields are solenoidal, that means they are of divergence 0, which is the case for incompressible turbulence. And if they are axisymmetric, then both of them can be decomposed without losing any generality, that is very important, into a poloidal and a toroidal component of the form below. Now any solenoidal field, vector field, can be decomposed in a poloidal and a toroidal component, but since they are axisymmetric, then this component should have a specific form, and that is coming from mathematical physics. Okay, one thing I have to tell you, that what really is a poloidal field and a toroidal field. Just imagine a torus like that, and there are two type of degrees of freedom on a torus. One is that along this like the axis of this. So if you cut the torus, then you will have a cylinder, then along this axis of the cylinder will be this direction. Okay, so that is the so-called toroidal direction. Okay, and if you take just this tube, basically this tube, the toroidal tube, okay, and you just calculate, I mean you just follow this degrees of freedom, which is along this lateral surface, okay, and then actually the axis will be exactly the axis of the cylinder. So here in the first case the axis was in the first case the direction was the axis of the cylinder, but the axis was this, okay. And in the second case, for the poloidal case, which we call poloidal, the axis is the axis of the toroid, okay, I mean axis of the toroidal cylinder. So this is roughly what poloidal field is, which you can see in blue, and what toroidal component is, which you can see in green. Okay. Now, for our case, velocity and magnetic field can be written in like this. Velocity can be written as omega, which should be a constant. It is something like a angular speed, times r, the radius vector, times phi cap, and this is exactly the toroidal component, plus curl of size scalar by r times phi cap. Okay, so this is the poloidal component. So this type of writing is very general for an axisymmetric solenoidal vector. Okay, and for B we can also write, since B we also can use the so-called vector potential of B, which is A, then we can actually write B is equal to some B times phi cap, which is the toroidal component of B, and the poloidal component of B is given by curl of the vector potential magnitude times phi cap. Okay, so this thing we can actually write. And now if we simply replace this expression for B in this B and also V actually in this induction equation, now you see in this induction equation we have this term, nonlinear type of term, which is no longer nonlinear here. This is the linear term here according to kinematic dynamo approximation, and you have another resistive term. The resistive term should have a plus sign, of course. Okay, and then if you do that correctly, you will see that for the vector potential part, you will have this, that the evolution for this vector potential is given by this del A del T plus 1 by R. Vp dot nabla, Vp is nothing but the poloidal component of the velocity. Vp dot nabla A is equal to eta times, okay, eta is this one, nabla square minus 1 by r square E. This is a scalar operator, okay, and this is a scalar equation. So the evolution of A is nothing but the evolution of the poloidal component of B. And then the toroidal component for B has an evolution equation, which is del B del T plus R times Vp dot nabla times B by R is equal to eta, again nabla square minus 1 by r square B plus R Vp dot gradient of omega. Now you see this omega is no longer actually a constant, this is a scalar. Okay, now you see in this point for A the solution is simple. It has an advecting component, but mainly its fate will be decaying because it has a diffusive component. Okay, now for what happens for the B? Now B has once again an advective part, one diffusive part which lets it to decay, but there is a source term. Now that can be something of interest, but the problem is that the source term is proportional to Bp and BP is nothing but proportional to A. Now with time A decays, so BP will also decay, so B will also decay. So the source term of B will stop in time, and finally B will decay just due to the action of this diffusive term. And that is why in this case, under this specific writing, that is very important, under this specific writing, the poloidal component decays due to the absence of any source term, okay, this one, and the toroidal component evolution has a source term, but this depends only on the poloidal part, and so it is stopping at one time because the poloidal, poloidal part, decays in time, so the source stops, and so finally the toroidal component also stops in time. Okay, so that's exactly saying that we cannot have a self-sustaining kinematic dynamo where both the magnetic and the velocity field are steady and symmetric about the same axis. Okay, then what can be possible? Then the thing is that in order to have a sustaining dynamo action, non-axis symmetric steady velocity fields or non-steady axis symmetric velocity fields, I mean any of the two conditions, steady and axis symmetric, is if violated can give rise to a sustaining dynamo equation. So they can sustain a steady axis symmetric magnetic field. But this needs rigorous mathematical treatment, and there are researches on it, there are papers on it, you can search over internet. And here for the scope of the, this is beyond the scope of this course. Here we will do another thing which is much more simple. So in this scope, in the scope of this course, we will simply discuss a qualitative description, or qualitatively the idea behind the Parker's turbulent dynamo. But Parker's turbulent dynamo is very, very important for this course because it has an enormous astrophysical importance. And actually, most of the astrophysical dynamos, okay, except solar dynamo, to be very honest, have, most of the astrophysical dynamo can in a very simplistic way can be understood using Parker's turbulent dynamo. So this is not a very, it's a highly useful theorem, okay, or a highly useful model, okay. But for that we again have to go to the traditional poloidal toroidal decomposition of solenoidal vectors. So in spherical coordinates, if we write any vector, let's say the magnetic field Br r cap plus B theta theta cap plus B phi phi cap, then this azimuthal component can be identified exactly to be equal to the toroidal component. The rest is nothing but the poloidal component. Okay. Now here our main objective of the study is to produce a sustained poloidal field, otherwise both poloidal and toroidal would decay, right? Just as we saw that the toroidal part, so the poloidal part, if it is sustaining, then this is sustaining, and then as this has a source which is related to the poloidal part, can also be sustained. So of course this is roughly true. We cannot talk about this model here, but roughly the idea is that if in any ways we can produce a sustained poloidal field, then actually poloidal and toroidal, they can sustain. Otherwise, if the poloidal field is somehow decaying, then poloidal field would stop, and the toroidal field would also decay in time. Of course, a bit it could continue a bit longer, but finally it would stop. Okay. Now Parker in the year 1955 in his seminal paper gave an excellent idea actually, a revolutionary idea on how the poloidal field can be generated. And at this point you will see that how useful for you was to learn turbulence, because Parker say that it is actually the turbulent motion of the plasma, okay, inside the astrophysical body which causes all this sustained dynamo action. According to his theory, the turbulent convective motion of the plasma in an astrophysical body stretch out the toroidal fields. Let's say the toroidal fields was originally like this, so this is actually in a perpendicular plane of the paper, okay, so you can easily understand, so it should be like this, okay, and then so this is the the azimuthal direction, just for example, okay, and then what happens that as there is turbulent convective motion, the body motion, and if the body has conductivity, effective conductivity, which is much larger than the viscous effects, so the frozen in field theorem is approximately valid. And when frozen in field theorem is valid, then the plasma would drag the magnetic lines of force, and actually it is seen that finally this can, so in two hemispheres, in one hemisphere it can make the lines of force up a bit, so it is like this, okay, and in another hemisphere it is like this, down, okay. So you will see, so exactly this picture can be seen over here. So finally, starting from some toroidal toroidal direction, we have something which is now non-zero in the poloidal direction as well, okay. Now there are other part of the story as well, that is, now most of the cases what happens that we are considering rotating frames of reference, and rotating frames of reference, you know that this adds to the vorticity of the blob of a plasma even if the initial vorticity is zero. That we know from the rotational effect of rotation in a rotating frame of reference, that the we do not, even for an incompressible fluid, we do not need an initial vorticity, but the rotation, the solid body rotation of the plasma itself gives the plasma a vorticity, okay, and that vorticity would evolve in time. Now once the vorticity is given, then magnetic loops are formed, okay. So the story is very complicated, it is just schematically said over here, and these magnetic loops get smoothed by the turbulent diffusion, which you already have learned. So when turbulent diffusion smoothen that, finally you will see in this type of thing you can have small magnetic loops, and actually very interestingly it can be seen that all the magnetic loops in both the hemispheres are of the same sense, okay. That's very, very interesting. Now this finally leads to the poloidal field, a large scale sustaining poloidal field. Now these poloid, so here we can see that the generation by turbulence, actually sometimes we say helical turbulence, because this is a turbulence with helical motion, okay. So by helical turbulence, toroidal fields can give rise to poloidal field. And again, if the system has a differential rotation, as we can see in sun, okay, so then again these poloidal field lines are stretched to give again toroidal fields by differential rotation. So this is the whole story of the turbulent dynamo, and sometimes some people call this as also the alpha omega dynamo. This is just for a vocabulary, although the proper analysis of alpha omega dynamo is not discussed here, and it is a bit much more analytically much more rigorous, okay. So that is something which I suggest you to check, okay, even in any of the books of reference, okay, or over internet, how can using mean field magnetohydrodynamics we can account for the possibility of a large-scale magnetic field by turbulent dynamo proposed by Parker. Okay, although once again, as I said, sun's dynamo, solar dynamo, actually cannot really be described by in this simple framework. Okay, this is something you have to understand just for as a basic tool of understanding astrophysical turbulence. Astrophysical dynamos. And also, well, now the question is, of course, what about Earth's magnetic field and what about Earth's dynamo? Okay, so once again, Earth does not have any differential rotation as such, but my question to you that can turbulent dynamo by Parker can shed some light on the Earth's dynamo problem, why this is sustaining? If yes, why? If not, why? This is also a very good homework for you, and so the take-home message from this lecture is that turbulent dynamo model, which I described here qualitatively, actually starts. This is just the starting point of the dynamo theory in its rigor. Okay, so the rigorous treatment is not done here, but just to tell you that already the very simplistic dynamo model includes so many pictures of rotation, frozen in field theorem, turbulence, rotational effect, everything. Okay, including poloidal toroidal decomposition. Okay, so you see, and of course the situation becomes much more complicated if the fluid is compressible. So a normal astrophysical fluid in a dilute interstellar medium is highly compressible. And how to do that? Then you even cannot do very simply this poloidal toroidal decomposition. Okay, so this course was just to give you a very brief overview of what are the building bricks of astrophysical fluid dynamics. Of course, in the scope of this course, I could have just told you maybe less than 0.1% of the whole story. Okay, and now it's up to you. If you feel motivated, you go to the research papers, you go to several books, you go to the videos. Okay, nowadays you have billions internet resources. Okay, so just search over that, and there is always a very big scope of doing theory and simulation. Okay, and observation is also very much popular already in astronomy, but theory and simulation, there are so many scopes possible. I strongly suggest you, friendly but strongly suggest you to just go through several problems which are done in the last 25 or 30 years. Okay, so thank you very much for your kind cooperation throughout the course. Okay, I personally may not have been able all the time to express the best possible way what I wanted to say, but you see that once again this was just an introduction. If you simply feel motivated by this course to the problems of astronomy or astrophysics, my work is done. I am more than happy. So thank you once again. Thank you very much, and best wishes, best of luck for the examination. Thank you. Bye-bye.